So Class C amplifier design example. In this amplifier, we want to drive the transistor hot enough to act as a switch. Any drive in excess of this amount is not only wasted power but also seriously degrade the efficiency by driving the transistor into deep saturation. Hence, we compute the maximum drain current required and then adjust drive conditions on the gate to provide this current and not much more. Again, our goal is to supply 1 watt into 50 ohms with a 3.3 volts DC supply, recalling that the maximum output power is P0 is equal to 0.577 V square dd by R. We compute that the desired load resistance is actually about 6.3 ohms, but we will transform to a 5 ohms load to accommodate various losses. The basic topology is shown in figure and the associated equations. Class E amplifier should be like this. Class C amplifier designing. So L is equal to QR by omega, C1 is equal to 1 by omega or into pi square 4 by 4 plus 1 into pi by 2 omega of r dot 5 dot 47447. C2 is approximately equal to C1 into 5.447 by Q. 1 plus 4 1.42 by Q minus 2.08, where R is 5 ohms and choosing Q is equal to 10 leads us to the following values. L is equal to that value C1 and C2. These values. The required impedance transformations may be provided by the simple low pass L match whose element values are given by Lm is equal to 2.4 nanohenry, Cm is approximately equal to 10.6 picofarads. Combining the two inductors into one leads to the final design shown in the figure. Next, combining the two inductors into one leads to a final design. In practice, the drain capacitance of the transistor itself would from the part of the 5.8 picofarads capacitance. More complete class C amplifier. Voltage controlled oscillator. What is an oscillator? An electronic circuit used to generate the output signal with constant amplitude and constant desired frequency is called as an oscillator. It is also called as a waveform generator which incorporates both active and passive elements. The primary function of the oscillator is to convert DC power into a periodic signal or AC power at a very high frequency. An oscillator does not require any external input signal to produce sinusoidal or other repetitive waveforms of desired magnitude and frequency at the given output. The waveforms are like this. We are giving the DC power to the oscillator and we are obtaining the AC output. And VCO is an electronic circuit whose oscillation frequency is controlled by a voltage input. The applied input voltage determines the instantaneous oscillation frequency. An oscillator whose frequency can be tuned by a voltage is called VCO. Voltage input DC power giving the AC output. The figure A shows the oscillator whose frequency can be tuned by a voltage performing frequency modulation. In FSK, square wave pulse is applied to the VCO, producing a broad output spectrum due to the abrupt changes in the VCO frequency. A common method of pulse shaping for frequency modulation employs a Gaussian filter, that is one whose impulse response is a Gaussian pulse. So generation of GMSK signals. Figure B shows the pulses applied to the VCO gradually change the output frequency, leading to narrower spectrum called Gaussian minimum shift keying and is used for GSM cell phones. In modern RFIC design, MOS varactors have supplanted their PN junction counterparts. A regular MOSFET exhibits a voltage dependent capacitance, but the non-monotonic behavior becomes limits design flexibility. A VCO employing such a varactor would generate an output frequency that rises and falls as VGS goes from negative to positive values. Now we see one common architecture for realizing VCOs in ICs. One common architecture for realizing VCOs in integrated circuits. The current stored ring oscillator, in which the effective propagation delay of each inverter in the ring is controlled by a current source. The controllable ring oscillator derives from the uncontrolled ring oscillator and consists simply of n inverters in a ring where n is odd. So, what is ring oscillator? In its simplest form, it appears as shown in the figure below. In n inverters, in the simplest analysis of such an oscillator, it is assumed that each inverter can be characterized by a propagation delay TPD. No stable DC point exists, and a logic level propagates around the loop, experiencing one net inversion each traversal. The oscillation period is therefore simply twice the total propagation delay. Now to convert this thing into an controllable oscillator, the propagation delay seems the most natural quantity to adjust. One such oscillator is a current storming ring oscillator. The propagation delay is adjusted by varying the current drives of the inverter. PMOS realizes a current mirror which a CMOS inverter and hence applies a finite variable current to it. The effective propagation delay of each inverter in the ring is controllable by current sources. DCOs realized in ICs incorporate the similar architecture of current stored ring oscillator. The effective propagation delay of each inverter in the ring is controlled by current sources. DCOs realized in ICs incorporate the similar architecture of current stored ring oscillator. PLL. Phase lock loops have become very important in modern communication systems because of their remarkable versatility. PLL may be used to generate an output signal whose frequency is a programmable rotational multiple of a fixed input frequency. The output of such frequency synthesizers may be used as the local oscillator signal in super heterodyne transceivers. Phase lock loops may also be used to perform frequency modulation and demodulation. The basic PLL architecture is shown in figure is a negative feedback loop consists of a phase detector and a voltage controlled oscillator. Omega of t is equal to k into v of t. Applying transform, we get omega of s is equal to k into vs. K is equal to w of s by v of s. Units k is equal to radians per seconds by watts. A phase detector is a circuit that senses two periodic inputs and produces an output whose average value is proportional to the difference between the phase of the inputs. The input and output characteristics of the phase detector is ideally a straight line with the slope called the gain and denoted by KPD. WKPD. For an output voltage quantity, KPD is expressed in V by radians. In practice, the characteristic may not be linear or even monotonic. It is a circuit whose average output is proportional to the input phase difference. Simple PLL, ideal reference phase detector VCO output. Addition of LPF to remove high frequency components generated by PD. Linearized PLL model. Input signal phase detector VCO output. Phase lock loop architecture. The basic PLL architecture is shown in figure consists of a phase detector and VCO. Input phase detector VCO and the output. The output is given to phase detector. The phase detector compares the phase of an incoming reference signal with that of the VCO and produces an output that is some function of the phase difference. The VCO simply generates a signal whose frequency is some function of the control voltage. The general idea is that the output of the phase detector drives the VCO frequency in a direction that reduces the phase difference, that is, its negative feedback system. Once the loop achieves a lock, the phase of the input reference and VCO output signals ideally have a fixed phase relationship, mostly 0 or 90 degrees. We are generally interested in the phase relationship between the input and output signals. In this model, the input and output variables are phases. Rather than that, in this model, the input and output variables are phases rather than the time waveforms of the actual inputs and outputs. Another consequence of choosing phase as the input output variable is that the VCO, whose output frequency depends on a control voltage, is modeled as an integrator since phase is the integral of frequency. The VCO gain constant KO has units of radians per second per volt. Detector is modeled as a simple subtractor that generates a phase error output, that is the difference between the input and output phases. To accommodate gain, scaling factors and the option of additional filtering in the loop, a block with the transfer function H of S is included in the model as well.